Today I talk about spectral theorem, one important theorem in functional analysis. We also discussed in previous class. Now we getting some observation from here. Okay, we write these observations one by one. So first we talk about NT perpendicular. NT perpendicular equal to span of phi 1 phi 2 dot. Okay, this closure, that means phi 1 phi 2 be the eigenvectors and this span perpendicular of nullity of T. That means this operator, null space of this operator perpendicular also represented by phi 1 phi 2 dot. That means this eigenvectors. Okay, so next we also write here by this projection, by the projection theorem, H equal to NT perpendicular, here NT direct sum of NT perpendicular. Okay, here is this sign, that means addition with respect to addition operator with respect to perpendicular. Okay, this equal to NT addition operator with respect to perpendicular, this RT closure. Okay, then what we talk about for this, the spectral theorem guarantees the existence of the orthonormal basis for RT closure. Okay, hence RT is separable. Okay, in addition, if NT is separable, in addition RT is separable means RT has a countable dense subset. Okay, in addition if NT be separable, then what happen, H be separable. Okay, H be separable. Now we also discuss option C. Okay, I will write, that means observation C, what we observe from the spectral theorem. Write H equal to NT direct sum of union of k equal to 1 to infinity gk. Okay, where Gn equal to Hn perpendicular equal to direct sum of I equal to 1 to n minus 1 nullity of T difference lambda I. Okay, then we also going to another conclusion. We also write Ht equal to nt direct sum of union of k equal to 1 to infinity jk where g and r h n perpendicular. Okay, equal to nullity direct sum of nullity of t difference lambda I. Okay, then we erase those and again write another observations. Erase our portion also. What we write now, here observations. First d we write here t of restriction of nt perpendicular equal to diagonal of lambda 1 lambda 2 lambda n. Okay, t a restriction of nt perpendicular equal to this. Okay, next we write another observation. We write in e each lambda j is repeated in the sequence lambda n. Is repeated in the sequence lambda n exactly pj equal to exactly pj equal to dimension of nullity of t difference lambda ji. Okay, this times exactly pj times, that means lambda j repeated in the sequence lambda n exactly pj times, that means nullity of t difference lambda j I dimension of this time. Since the sequence lambda n tends to 0, each lambda j appears finitely many times. Each lambda j appears finitely many times. Finitely many times. Okay. Let lambda j equal to lambda ni I equal to 1 to dot 1 to dot p. Then nullity of t difference lambda j I equal to span of phi n1 phi n2 phi np. If this is not possible, if this is not possible, if this is not possible, that means nullity of this not equal to span of this, then there exists 0 not equal to v belongs to n of t difference lambda j I such that v perpendicular phi n I for 1 less than equal to I less than equal to p. If k not is equal to ni, 1 less than equal to I less than equal to t, then v perpendicular phi k as lambda j not equal to lambda k. Okay, hence lambda j v equal to tv equal to summation k lambda k v phi k equal to 0. Since v perpendicular phi k, so v phi k equal to 0, which is impossible, which is impossible, impossible. Okay, because lambda z not equal to 0. Since lambda z not equal to 0, because lambda z not equal to 0 and v not equal to 0. Okay, so this is not possible. Now we erase this portion and going to further discussion about something. Okay, we write these observations, okay, in a suitable way. Now we're also going to further discussion about some topics. Now we erase this portion. Now define d L2 to L2 is given by d of x1 x2 x3 equal to x1 x2 by 2 x3 by 3 where x1 x2 x3 belongs to L2. Then t belongs to then t belongs to kh. Okay, that means t be compact operator we also discussed earlier, and b also self-adjoint. In previous class we also discussed that. Now note that d of en equal to 1 by n en. Okay, hence 1 by n is an eigenvalue. Hence 1 by n is an eigenvalue with an eigenvector en. With an eigenvector en. Also 1 by n tends to 0. Also 1 by n tends to 0 as n tending to infinity. We can also represent d as d of x equal to summation n equal to 0 to infinity 1 by n inner product of x en for all x equal to xn belongs to L2. Okay, then we also give some example which also we discussed in earlier, but here we also represent dx as in this way. Okay, inner product of xen 1 by n xen en. That means by this theorem, by this spectral theorem we also write this one. Okay, now we also going to another observation. If k equal to kh, then r of k difference lambda I range of these is closed for each lambda. For each lambda belongs to C difference 0. This one observation. If k is, then R range of k difference lambda I is closed for each lambda. Okay, so we erase that portion and going to discussion about one theorem. Now we write one theorem. Okay, we first write one statement of this theorem. Suppose that phi 1 phi 2 phi n phi 1 phi 2 phi n is a sequence of orthogonal vectors in H. Orthogonal vectors in H and lambda n and lambda k be a sequence of real numbers such that lambda k is finite or converges to 0, then the operator defined by tx equal to summation k equal to 1 to infinity lambda k x phi k inner product again here phi k is compact and self-adjoint. Okay, how we discuss this one? We also talk about phi 1, phi 2, phi n are orthogonal vectors and lambda k be the sequence of real numbers is finite, converges to 0 otherwise. Then the operator defined by this one is compact and self-adjoint. We have to prove that. So start with prove this. We also start this proof. We consider the following cases. We consider the following cases. First case we marked as case 1. Okay. Then the lambda k be finite. If lambda k be finite, then consider tx equal to k equal to 1 to n lambda k x phi k inner product here phi k. Okay, then norm of tx square equal to inner product of tx equal to summation k equal to 1 to n norm of lambda k square x phi k mod square, then less than equal to maximum of k lambda k here norm x square. Okay, then this shows that This shows that T belongs to BH and T is a finite rank operator. Is a finite rank operator. Okay, hence TV compact. Hence TV compact. Okay, then we also discuss next topic. If lambda k be finite, then obviously tx equal to this. Norm of tx square equal to inner product of tx equal to summation k equal to 1 to n lambda k square, and this one here in norm of that means x phi k and x phi k uh, mm, conjugate, then this one is norm mod of x inner product of x phi k square less than equal to maximum of lambda k and norm x square. This shows that T belongs to BH and T is a finite rank operator, then hence T be compact. Okay, now case 2, we erase total portion, then going to further discussion about that. Case 2, lambda k is infinite. Lambda k is infinite and lambda k tends to 0 as k tends to infinity. Okay, by the spectral theorem, by the spectral theorem, we get norm of tx square equal to summation n lambda n square mod of x phi n norm square less than equal to maximum of k greater than equal to n lambda k norm of x square. Okay, then hence norm of t, hence norm of t less than plus infinity. Now define t in x equal to k equal to 1 to n lambda k x phi k in a product of this phi k, then t difference t ins norm this square equal to supremum of norm x equal to 1 norm of summation k equal to n plus 1 to infinity. Here lambda k x phi k norm of this square equal to, then what happened, then this less than equal to supremum of lambda k square. Okay, why we talk about this, because norm of this one is less than equal to supremum of lambda k square and norm x square, then norm x equal to 1, so we write this thing where k greater than n. Okay, here t, because tn is this and t equal to summation k equal to 1 to infinity, so just this one is remaining. Okay, next we talk about this one tends to 0 as n tending to infinity. Since lambda k tends to 0, let's get n to infinity. Okay, here intended k tending to infinity. As is Tn is finite rank, is Tn is finite rank. Okay, here is Tn is finite rank, then and hence compact. Hence compact. So T is compact. So T is compact, and it easy to verify that it it is easy to verify that T equal to adjoint of T. Okay, so we also do this proof. Okay, then obviously we erase this one, but if we how we verify T equal to T star, this one also, that means one questions. If we check about it, we also see that how we do this. Here Tx equal to summation k equal to 1 to n lambda k x phi k phi k. Okay, then if we write txy, this one, then this one equal to this lambda k x phi k phi l phi k y. Okay, then this one equal to, if we write here x dy, then what happened? Then sorry, we write later. Here this one equal to how much? K equal to 1 to n lambda k x phi k, here phi k y. Okay, and y t x, sorry, here x t y equal to how much? Here also x, here summation k equal to 1 to n lambda k y phi k, and here phi k. Okay, then this equal to k equal to 1 to n lambda k y phi k and x phi k. Okay, y phi k is, and obviously this, then this equal to k equal to 1 to n lambda k, and here phi k y x phi k. So how, why this one equal to this one, but lambda k are real, so this one is possible. If lambda k is real, then this one is possible, otherwise this one is can't be possible. TV cell adjoint. So here obviously lambda k is finite given, so this one is real, so this one is done. Here real numbers also given. Okay, so this one is done, so we write to talk about that. That means txy equal to inner product of x d star y equal to x dy. Okay, so t star equal to t, that means adjoint of t equal to t. Okay, so today we discuss this portion. Now we also have some portions is left, one important theorem and also one definition. This one we also talk about in next class. Okay, so today we stop here.